Hello everyone, welcome to Study EETech. In this video, we will learn how does a full wave circuit operate. But before coming to the circuit operation of full wave rectifier, let us see what are the type of circuits. The full wave rectifier can be classified into two. One is called the center tapped full wave rectifier and another is called the bridge full wave rectifier. They have their respective advantages and disadvantages. We will see one by one. First, we will come to the center tap full wave rectifier. This circuit diagram we see here, the input is connected to the primary side of the transformer and the secondary side of the transformer. There are three terminals, this one and the center point. We have connected diode D1 at this terminal and the cathode is connected here, and at this terminal D2 is connected and the cathode is connected here. Basically, at the two extreme ends, two diodes anode are connected and the cathode are joined together, and the load is connected in between this common cathode terminal and the center point. And this is called the center tap transformer, and this is our center tap full wave rectifier. Now we will look what is a bridge rectifier. In case of bridge rectifier, we see there are four diodes D1, D2, D3 and D4, and the load is connected between these 2 points, the common cathode and the common anode. And in the first leg at the midpoint and the second leg at the midpoint, the two terminal of the AC supply is connected in this way. And this is our bridge rectifier. Now first we will take center tapped full wave rectifier and we will understand the operation in details for this circuit. Then we will take this one. So the operation of the center tapped full wave rectifier is this one. The circuit diagram we have already seen. Now, as because the input voltage is a sinusoid, the polarities of this input voltage will keep changing positive, negative, negative, positive in the positive half cycle and the negative half cycle, right? In the positive half cycle, the scenario is this one, where we see this terminal voltage is positive and this terminal voltage is negative. And we are assuming this is the dotted terminal of the transformer. So we can say this terminal voltage will be positive and this terminal voltage will be negative. Now, unlike the previous one, we have the center point. So we can say with respect to this positive terminal, the center point is negative, and with respect to this negative terminal, the center point can be considered as a positive. So if I take this part only, here this is positive and this is negative, higher voltage and lower voltage. And if it is so, looking at this circuit diagram, we see anode of this diode D1 facing the positive voltage and cathode of the diode is facing the negative voltage, right? And in case of D2, the anode of the diode is facing the negative voltage and cathode of the diode is facing the positive voltage. So we can say the diode D2 is in reverse biased mode and diode D1 is in forward biased mode. So we can replace the diode D1 by short circuit and the diode D2 by a open circuit, and our equivalent circuit will look like this. And the load terminal A and the load terminal B, the load is facing the voltage of half of the secondary voltage, right? Out of this full voltage, now we are getting half of the transformer secondary voltage. Now the scenario will change when we take the negative half cycle. In the negative half cycle, this positive and negative, they will alter, and this terminal voltage now is negative and this terminal voltage is positive. And obviously this terminal voltage will be positive and this terminal voltage will be negative. Like the previous, here also we can say with respect to this positive voltage, the center point is negative, and with respect to this negative voltage, the center point is positive. Now if we think about the diode D1, the anode is facing the negative voltage, right? And the cathode is facing the center point, which is with respect to this negative is positive. So diode D1 is in reverse biased mode. The anode is negative and the cathode is positive. Similarly, we can apply the same concept here. In case of D2, the anode of D2 is facing the positive voltage and cathode of the D2 is facing the center point, which is negative with respect to this. So we can say the diode is in forward biased mode. So now we can replace the diode with its equivalent circuit in the forward biased state and the diode in its reverse biased state as the open switch. So now output voltage is facing the half of voltage, the lower half of the output voltage is appearing at the load. Point to note down here, the A voltage is positive, the B voltage is negative here, and also in the second case the A voltage is positive and the B voltage is negative, right? So coming to the next slide, we see here the two equivalent circuits are shown in this way. This is the equivalent circuit of the positive half cycle like previous, positive and negative. So this voltage is positive, negative. I have shown in different color to explain you that Vi1 plus Vi2 constitute the total secondary voltage. So this is our input voltage which is fed at the primary of the transformer, and in the secondary we are getting two voltages. This one is red and this one is blue. V1 and V2 we are getting in this way. Now if so, in the positive half cycle we have already seen we get the voltage V1, and in the negative half cycle we get the voltage Vi2, and the output voltage will be this one. I have shown the positive half cycle voltage we are getting from V1 as the red color 0 to pi, and in the negative half cycle we get the voltage from Vi2 which is the blue color. And considering the input to be continuous sinusoid, and from 2 pi to 3 pi, 3 pi to 4 pi so on, we will get this sort of output voltage as the input voltage is a sinusoid. So unlike the previous one which was the half wave rectifier, here we are getting the output voltage in both of the half cycles. In the positive half cycle we are getting the voltage, in the negative half cycle also we are getting the voltage, but in each cycle we are getting actually half of the secondary voltages, right? This is the point to be remembered here. Now we will see the operation of the bridge full wave rectifier. The circuit diagram is this one we have already seen, where 4 diodes are connected in this way. Now in the positive half cycle this voltage is positive and this voltage is negative, right? So what we can say, out of this D1 and D3, D1 will be forward biased because positive voltage is this one and the negative voltage is this one. So D3 is reverse biased and D1 is forward biased. This can be actually explained in another way. These two diodes are connected in common cathode, and in case of common cathode that diode will be forward biased, which is having the highest potential between these two. Because positive is higher than the negative, so the diode D1 will be forward biased. And similarly, in case of common anode configuration, we can say that diode will be forward biased, which is having the least potential at their respective cathodes. Between this one and this one, this is low, so D2 will be forward biased. In case of positive half cycle, we will replace the status of the diode in this way. D1 is forward biased, so it is replaced by a short circuit. D2 is forward biased, so it is replaced by a short circuit, and D3, D4 both are reverse biased, so they are replaced by this open switch, right? Then we will get the output voltage to be positive and negative, because this positive voltage through this path will appear here at the point A, and the negative voltage will appear through this path at the point B. And if we measure the voltage of A with respect to B, we will get the output voltage to be equal to the input voltage. Now in the negative half cycle scenario will be just reverse. Now this voltage is negative and this voltage is positive. Now we can say D1 and D2 will be reverse biased and D3, D4 will be forward biased. Same logic can be applied, common anode and common cathode. So we can replace the diode D3 by the short circuit, and we can replace the diode D4 by a short circuit, and D1 and D2 with open switch. Now what will be the load voltage? Now this positive terminal voltage in the negative half cycle through this path will appear at the point A, right? And the negative voltage through this path will appear at the point B. So we see that in both the cases, positive half cycle and the negative half cycle, we get the output voltage to be positive, negative, positive, negative. This is possible only due to the bridge connection. And this is the operation of the bridge full wave rectifier. Now we will see the waveform of the bridge rectifier. This is the input voltage, right? And we will get the output voltage to be the positive, positive, positive and the positive. Though the input voltage keeps changing, we will get the output voltage to be always positive. Unlike the previous one, There is no transformer involved here. Obviously, this input voltage will definitely come from some transformer, but for the sake of rectification purpose, we do not require a transformer here. So directly the input voltage will appear at the output as the full voltage. No half of the secondary transformer will appear at the load, unlike the previous one, which is the center tapped full wave rectifier. So this is the operation of the bridge full wave rectifier. And we have seen how does a center tapped full wave rectifier operate and how does a bridge full wave rectifier operate. Hope you liked the video. If you are new to this video, let me tell you this is about us and we need a little bit help that will keep us motivated to make new contents and better contents. So please subscribe to our channel and follow our Facebook page. Visit our website also. Thank you.